Howdy folks, Tom Bubbler here again with the Noble Ape simulation source code walkthrough. I'm going to intentionally avoid ApeScript for the time being, just because it's probably the most complicated. If you thought the file handling was complicated, ApeScript is going to be considerably more complicated in terms of how the underlying stuff within ApeScript works. That only leaves Noble threads in the Noble directory, and basically that does nothing currently. That's going to handle the atomic threading in the future, so not a lot to talk about there. So let's move on to the core directory, and this is the Noble Ape simulation course specifically. I'm going to start with land.c. Historically, land.c is probably the oldest source code within the simulation. It handles the land, it also handles the weather. The weather is a relatively modern addition. I had written a weather simulation separately from the Noble Ape simulation land data type. I want to say probably 2001, but it was only fully integrated in the simulation sometime in the mid-2000s, so I'm not sure when it was actually introduced, but that's what the source file kicks up with. And let me describe the weather simulation initially. So the idea of the weather simulation, it has a kind of directional pressure component, which is supposed to mimic the wind, and it has kind of bleeding pressure component, which is just simulates the nature of air pressure and the kind of transitory nature of air pressure. So there, as with the cognitive simulation, there are two competing effects. One being a kind of spatial effect and the other being a directional effect from the wind. And my hope was at some stage that the cognitive simulation and the weather simulation could actually be brought together, so maybe that's where that comes from. The idea in the weather simulation specifically is that you have these kind of pockets of humid air that are pressurized and become clouds, and then even more squeezed and become rain. So the difference between kind of clouds and rain is just an increase in kind of transitory pressure. I should also, I mean, it's going to start with weather cycle, but it's probably better to start with weather INIT just to give some background. So I'm actually going to do this out of order and go to weather INIT first. There's a lot of error handling, which I put into the simulation, and here it doesn't really do anything, and I need to really step back and remove some of it. So you'll see show error, land unset, weather unset. I guess at the time when I wrote this initially, error handling uber alles was kind of the background. There are never going to be any circumstances where the weather's going to hit this. I think I probably actually added it at a time where there was some talk about the simulation being exported to various libraries, and I just wanted to basically protect this stuff, but really that error handling shouldn't be there. I'm talking about line 96, weather INIT, in land.c for folks who are scrambling to find it. Obviously, with regards to weather simulation, and particularly with regards to pressure mapping, the land surface is going to be one of the most important parts of constructing these pressure troughs, almost flow points, really, with regards to how the weather moves. And these are the two things that are set up in the atmosphere. The atmosphere contains both the kind of flow information and also how the pressure is affected at various points. So this is really the idea that the weather exists with a kind of land underneath and almost like a glass ceiling on top where this pressurized water vapor is kind of forced through, and where it's squeezed becomes clouds and then rain. So that's probably the easiest way to describe it. So the first thing we need to do is actually create a kind of rounded down version of the land. Now, the weather simulation is based on a grid which contains underneath it 2x2 of the land simulation. I should probably describe the variables. There is a transition between what is displayed on the screen, which in the map, which is a one-to-one, obviously, mapping of the land variables onto the map on the screen. And then for the Noble Ape's movement, there is in fact a far finer gradation. So there's this whole notion of coordinate and map throughout. But in the case of the weather simulation, the weather is actually two of the map points, either y equals one of the weather points, and the way it's displayed on the screen with regards to 2x2 dithering, makes it look like it's a one-to-one mapping from the land to the weather. It's not. Large reason for that was that there's so much calculation associated with the weather that if I did a one-to-one mapping with the land, it just didn't look right. And there are various other noise effects that come through the weather as well, and when there was a one-to-one mapping with the land, those noise effects were greater. There needs to be some kind of dampening almost because it's an integer weather simulation, but I probably said too much already associated with the weather simulation. Weather INIT, it needs to create a rounded view of the land 2x2, then normalize it around 0, which is why there's a kind of total land idea that's then normalized around zero and expanded. Then you have the flow patterns over the land, and this is an idea that basically the pressure channels find it easier to move through particular gradients of the land, and this is the second section here at line 129, which sets up an array of, it's a dx dy over the pressure. So you're taking a differential across one, differential across the other, combining those two, which is almost like a slip coefficient associated with how the weather will move over those sections. Another point I should make about the atmosphere is that it's really two separate arrays that are combined into one through this weather mem macro that just goes through and allocates it either in the kind of flow component or the underlying pressure component. So really it's almost a vector. I mean, the irony is one is really a scalar and the other is a scalar representation of a vector, and it works out. Having said that, with regards to how the land is mapped onto the atmosphere, it's then cleared at 129 because it doesn't actually need that information. The slip coefficient is all that it really needs, and it can use the part of the array that was previously used for the average land height as the actual weather pressure simulation component. So it was only rounded down by the 2x2 land points initially in order to create the slip coefficient, and it will use the area that previously contained the land to contain what the weather actually is. And here you see 256 cycles of the weather simulation, which actually just kind of constructs the weather from this very flat surface as it runs over these various slip coefficients. We've looked at weather INIT first. Let's go back to weather cycle. Maybe actually weather cycle has to occur prior to weather INIT because of the fact weather INIT calls weather cycle, so that's why it's that way. More protective stuff associated with just in case, this is used externally. We're back at line 62. I'm just explaining the show error. There's an idea of a total pressure because basically the pressure system needs to be renormalized, otherwise it will get weighted plus or weighted minus. So there's something that calculates the total pressure, and the weather is recalibrated based on that. So there's something that increments the total pressure. There's a local delta, which is the previous total pressure spread out over 128, so that's like relative across. I'm not sure how that weighting came in. And then you have the atmosphere, which is in integer, not necessarily just plus, but plus minus integer 32-bit values, which is how the atmosphere is represented. Okay, so it's creating a gradient differential from a single point on the x and the y, and then it kind of smears across, picking up the trough. This also is used in the land creation. We'll get to that in a minute. But it kind of smears across, working out the gradient, and basically it's constantly pushing the weather across the view that the slip coefficients kind of allow for that kind of transition. If we go to the local ATM, the local atmosphere pressure set at 79, let me try to explain this for you. You have the slip coefficient that's associated with the point, subtracted by the delta vector plus, subtracted by the delta vector minus, added by the delta vector minus. So these are a series of scalar to vector transitions which basically slip the weather over the slip coefficient with the various weightings. At the end of all of this, when it's renormalized in the equation, you find the amount of slip that has basically been pushed over the weather from this transition, and it's put back into the localized weather memory. This is almost an area diffusion screening method in terms of maintaining the same array to do all of this. As you'll see later, the land is done slightly differently. There's a paper in the way the weather is calculated in the Noble Ape simulation, so my apologies associated with all this kind of math and related stuff. In fact, I have been contacted by meteorologists that wanted to use the Noble Ape weather simulation as a kind of blueprint test back. So I don't know how I'd expand it. Probably rewrite everything in formula notation and include that. Like I said, the weather simulation was written 2000 through to about 2002, and a lot of the underlying math and stuff like that was kind of tweaked over that period, so I need to do some heavy head scratching, but the math is there. That's how it works. I think probably the description with regards to the pressurized water vapor and the ideas of kind of slips over the land and these kind of things, the glass ceiling and the pressurization, moving to clouds and to rain, probably gives some indication of how the weather operates. We move down weather pressure. This is a function that basically just returns the weather pressure at a particular point, again, libridized, if that's even a word, so that if it's used in a library and someone did something dopey, I should start if-defing protecting all of this stuff. I mean, my own feedback here is that this really isn't necessary in terms of all this protection within the simulation itself. But, it's written here just in case it's used in a library. Well, maybe I need to strip that code out because it's all getting compiled and all this nonsense is kind of propagating. So maybe I'll strip that out with an if-def in the future. Land weather reports. Okay, so the Noble Ape simulation was originally written with a global weather system that related to the time of year, which meant that as it was originally an island, the weather would flip through based on the time of year that it was and various potentials around that time of year in terms of sunny, rainy, what have you. So there's an underlying thing about day and night and kind of weather, which ultimately produces the icon that you see associated with day-night kind of weather. So when I introduced the weather simulation, and this is actually based on the specific point that the ape is at the simulation, the selected ape is in the simulation, it needed to report back a variable that was akin to this. I want to say, it's 0 to 6, isn't it? Because 6 is like the dawn-dusk thing that only occurs for a short period of time, doesn't have any real meaningful weather information. But everything else has, rain, sun, what have you, associated with whether it's day or night as well. So land weather, clocking in at line 171, basically reports back in this kind of old-style Noble Ape format about, is it raining, is it cloudy, is it day, is it night, and just produces it in the old icon format, so that's why that function's there. We now get to land cycle at line number 210. Land cycle is probably the oldest function in the simulation. And all this does is it just basically adds a minute onto the time and goes through, works out whether it's a century, works out whether it's a day, does all that kind of stuff. It's a relatively simple function to read. It's just basically about incrementing time and then, if need be, incrementing date. Not a lot going on here. When I say that the Noble Ape simulation's biology is defined in quantum mechanics, the ecology of the simulation is defined in quantum mechanics, we are now at this section. It starts at line 234, and this basically describes the quantum mechanical operators that are applied to the land variables in order to get the biological properties back from the simulation. That being said, let me try to explain this to you. Okay, so you have a landscape which is effectively, it's not a wave function anymore. When the simulation was originally written, it was just an island, it was a wave function. Now it's, we'll get to that in a while, but it's basically almost like a fractal, rounded landscape. Over that landscape, you can still get operators from quantum mechanics out. These operators contain, they're fundamentally area, height, water, sunlight, and moving sunlight. So that's total sunlight versus moving sunlight. And these operators are based in quantum mechanics ideas of a wave function that you calculate these things like area. Height here is specifically, as it's reported here, it's actually the height relative to the water. Actually, no, it's the height relative to the water squared. So yes, a lot of these things are squared, which is the nature of quantum mechanics operators for some reason are squared versions. So you don't get, rather than getting plus minus variables, you just get positive 0 to positive variables, and I maintain that particularly because we're dealing with population numbers, so you don't want a circumstance where the population numbers are negative. It has no real meaning in this context. Here the operators are constructed. Just prior to that, let's look at line 242, is the idea that it's a string array. I mean, it's just an array of bytes basically where things are either plus or they're minus. And as you go through, you see area, height, water, moving sunlight, total sunlight. These are the possibilities. These are set up initially with the operators. And then from that, bush, grass, trees, insects, mice, parrots, lizards, and eagles are all constructed from these underlying operators, either in a plus or minus version. Operators, a constant array of bytes, actually does a lot, because what it does is it describes what makes a bush, what makes grass, what makes trees, what makes insects, mice, parrots, lizards and eagles are all described in terms of what initially appear to be quite abstract ideas. And what you'll note here is that the moving sunlight is only applicable to the, I don't want to say living creatures, only applicable to the animals, the things that move, whereas the sunlight over time and other static or stationary operators are applicable to the plants, and that makes some logical sense, one would hope. So then we get into the land operator at 271, and what that does is it takes the map point, it takes the, what I'm calling DF or DG. The original Noble Ape simulation had an idea that there were two Fourier, that means they were made up of sine waves, I think just sine waves initially, multiplied together, and one was called F and one was called G, and one went along the X. I'm assuming F went along the X, G went along the Y. This naming convention continues forward with FG, even though this is just, the landscape has no connection to the legacy Fourier. It's just F and G, basically, they're directional indicators. So where you have DF, it's effectively DX with the Y, and where you have DG, it is DY with the X. As you'll see here, you take the local X, local Y, which is FG, DFGG, which is a step in the X direction, FDG, which is a step in the Y direction, and so it begins. So to make DF and GG true, you've got to subtract the F and the G, which is 281 and 282 lines respectively. The FG is then normalized against the water map, which gives some positive and negative, although, as you'll see, that all gets worked out in the wash. And then the operators are applied specifically. First one, area operator, next one, height operator, next one, water operator, and then it gets interesting because you have the time of day, you have the sunlight as it transitions over the landscape. Ironically, the function associated with that, I think, if I remember rightly, the landscape only applies to one direction. Let's have a look at the sun operator. Yeah, it's only working in the DF, so it's only working across the X-axis, so the sun scans across the X. For the moving sunlight, as it casts a shadow going across the X-axis is what it does there. And finally, the total sunlight, which has its own operator. All these things are taken together. There's then this idea of number of sums, which means that as you add the operators together, it kind of quasi-normalizes it based on how many things were added together. So if you have, for example, moving sunlight, water, and surface area, then you'll have three things additive. They should be pre-normalized, which means you just divide it by 3 to get a relatively normalized operator out. And that explains how you can get all these plants and animals out of just the land surface using the Noble Ape simulation methods in quantum mechanics. So that was relatively easy. Currently heavily utilized by ApeScript. Aside from that, very minimal use. So we now get to the land initialization, which is very interesting because it actually creates the land. And how do I explain this? Okay, so you have underlying this idea of random numbers which are taken from two genetic seeds which create the landscape. The landscape is flipped initially between two large arrays with the view that initially the landscape was, like I said, generated with sine waves, and then I started working in these ideas of how you could divide the landscape progressively in 2 by 2 and then 4 by 4 and then 8 by 8 and progressively finer areas with the view that the random number generator would then add and subtract these things, and that produced a very straight, produced a reasonable looking landscape, but you could see it was based on underlying blocks. And then I decided that what I needed to do was include a 45-degree, again, binary division, but do that in, I think, odd cycles from memory. Describing how the landscape generation works is relatively non-trivial, bar to say that you have these ideas, these big squares that are progressively getting smaller, that are then either added or subtracted to based on the random number generator as it gets to a smaller and smaller resolution. There's also this 45-degree addition that's put in there. I don't know, you might want to call it fractal, you might want to call it a wide variety of things, but basically it perturbs the landscapes with the view that it's also being rounded at each iteration, and this is why the map variable is swapped backwards and forwards. Between the back and forth there's a scratch variable, just so you don't have a situation like the weather where it's iterating over the same array. If that makes sense to you, more power to you. If it doesn't make sense to you, I probably could expand on this in its own time frame. It's relatively difficult to describe in the source code sense, but that's basically what it does. And you can go through the source code in parallel and try to work it out. That is land.c. Slightly less than io.c, but that's the land. We'll do a couple of the others shortly, but for now, Tom Barbley signing off.